you approach.
What is the significance of eigenvalues? Do we have time for that or no?
No. I'll tell you what they are, but in application they pop up.
Sure, what are they?
So eigenvalues and vectors.
We got time for that.
All right. So we say that a matrix has eigenvalues and corresponding eigenvectors to those eigenvalues. So it's defined in terms of a matrix. So given some matrix A, we define its eigenvalues, which we call lambda sub I. That's what we were doing before. Lambda sub I, and their corresponding eigenvectors. And eigenvectors v sub I as values and vectors that satisfy the following. Okay, so matrix multiplication, A times the vector v, if that matrix product is a scalar multiple, and it could have been called K or A or C or anything else, but is a scalar multiple of that vector itself. Okay? So if there is a value of lambda for which that's true, then that value lambda is called an eigenvalue. And the corresponding vector v is called its eigenvector.
Is that a lambda I versus eigenvalue?
Lambda sub I, yeah. Because there may be multiple eigenvalues to a given matrix. Okay?
It's like the plus or minus 5 that we had.
Right. Yeah, we did find eigenvalues. We didn't tell you what they were. Tell you that in that name. Okay, so the question is, how do we find them? Okay. From equation 3 right there, I could subtract lambda v from both sides. So a lot of things you could do, algebra, linear algebra, you can, a lot of the same, addition, subtraction. I could subtract lambda v from both sides, and that's equal to 0, but the 0 vector, right? Now, another thing that works is distribution from one side or the other, because matrix multiplication is not commutative, but distributive property from one side still works. So I could write this as A minus lambda times V, oops, don't want to put an arrow on it necessarily, equals 0, 0 vector. Oh, I jumped a step ahead. I want lambda I in there. One thing about some of these linear algebra proofs and derivations is that, remember this identity matrix? Identity matrix times anything is just itself, so I can slip in an identity matrix there. Equals 0. Because the identity matrix times V equals V. So I could put that in there. It's just like adding a 1 as a multiple of something. Okay?
So what's the purpose of putting the A in there, or the I in there?
Oh, because this is how we're going to find them. So right distribution of that vector V says I could write this as A minus alpha I lambda, not alpha, lambda I V equals the 0 vector. Okay? So call this equation 4. And V is a vector of values, if it exists. And if this matrix right here multiplies to give you the identity of the 0 matrix, then it must be that this, the determinant of this, is 0. Okay? Not important where that comes from, but from linear algebra, from a theorem.
Dumb theorem.
Okay? The determinant of that matrix must be 0. It must be singular. A minus alpha I must be a singular matrix to multiply to that vector V and get zeros everywhere.
It must be a zero, but that wouldn't happen.
What's that?
That must be a zero, but it never would be zero, right?
Right. They have to be linearly dependent for that to happen. All right. For this to be true, the determinant of A minus lambda I, again, just writing it this way, A minus lambda I must be identically zero. In other words, A minus lambda I is a singular matrix, is what it's called, for that to happen. Okay? So we find the values by computing the corresponding determinant. So let's find the eigenvalues and their corresponding eigenvectors. Of this matrix, A, 4, 2, 1, 3 in that order. Okay? So we start by finding the eigenvalues. And we use this, we use the fact that the determinant of this must be 0. So start with A minus lambda I times V equals 0, which implies that A, 4, 2, 1, 3, minus lambda I, and the I identity matrix 2 by 2, 1, 0, 0, 1. All of that times the value or vector V equals 0. Okay.
So every time you're putting a bar over the V,
It's vector, yeah.
it's considered vector, not the bold or whatever.
Well, I'm trying to be get it, yeah, bold. That's not bold. I actually put a little tip on that one. I usually do that in Calc 4 or whatever, but so same thing. Same thing.
If
All
you
right.
make it so that it's an arrow, it looks less like it's like an average.
Right, that's true, huh? Yeah, average of V. We have no context. All right, so now what does this matrix look like? A minus lambda I.
4 minus lambda.
So multiply, scale this by lambda, and subtract corresponding entries. 4 minus lambda. 2 minus 0 lambda. 1 minus 0 lambda. And 3 minus lambda. All right. So then by that theorem,
So that's why our determinant's not going to be there. Or wait, determinant will be zero.
it has to be 0 for this to be true in general. Okay?
Because, well, because that's a,
If
Why
V
do
is
you-
if V is a non-zero matrix,
oh, because Z is a non-zero matrix.
yeah, it is in general. Yeah, we're not assuming that it's the 0, or does sorry, if V is not the 0 vector.
Because timesing a matrix by a matrix determinant is 0, what is 0?
For this to be true, unless V is all zeros, in order for this matrix product to equal 0, the rows of this have to be linearly dependent,
Gotcha,
which means the determinant is 0.
gotcha.
All right. So by the theorem, then, we know that the determinant of that matrix, 4 minus lambda, 2, 1, 3 minus lambda, is equal to 0. Okay? So now, so this is what we do. We could often, you could skip steps and go to this matrix, right? A minus lambda I, and write that matrix down. All right. And we're going to find its determinant, right? and set it equal to 0 and find out what values of lambda make that true. So this is going to be 4 minus lambda, determinant of a 2 by 2 matrix, product of the main diagonal. 3 minus lambda minus 2 equals 0. Okay? And then we multiply this out. 12 minus 2, I think we're going to have a plus 10. I have a lambda squared. Right, lambda squared minus 4 lambda minus 3 lambda plus 12 and minus 2. Okay? All right.
-5, -2?
Yes. So this does factor. -5, -2, but that means the solutions are opposites of those, right? So lambda is going to be equal to 2 or 5, 2 and 5, right? So we got 2 eigenvalues, right? By the way, sometimes this is called the characteristic equation of a matrix. Okay. So it's a polynomial only involving lambda, and this is called the characteristic equation.
What are the ones left? What does it matter?
Well, they're all the same. So characteristic equation of the matrix A. All right. So it's a polynomial in lambda. If we solve it, we get 2 values, potentially complex values. You could have complex eigenvalues. All right. So let's look at the eigenvalue. Let's go in order. Let's look at the eigenvalue 2 to find the eigenvectors. All right, so for lambda equaling 2, let's see, following that equation. Okay. Oh, right, this one, 4. All right, so from equation 4, we get the original, 4 minus lambda. If lambda is 2, then we get 4 minus 2, 2, 1, and 3 minus lambda. Lambda is 2, so that gives me let's write it all in there. 3 minus 2. Times v equals the 0 vector. All right. So in other words, and let's do this one more step. 4 minus 2, 2, 2, 1, 1. Times v, and we'll just call it AB for now. I don't know what these are. Equals 0. All right. So what equations does this give me? By the way, this is going to be v here, my eigenvector that we're looking for.
2a minus
2a plus 2b equals 0. And 1a plus 1b equals 0. Oh, what do you notice about those equations?
That it's a matrix that we can solve for.
Well,
And here's 0.
what's that?
And here's 0.
Well,
It could be -1 and 1.
A is opposite B. What do you notice about the top equation though? It's a scalar multiple of the second equation. Right. Because these rows are linearly dependent. We found the values of lambda that made that happen. That's why the determinant is 0. Okay. See this determinant of this matrix? 2 minus 2 is 0, non-singular. So the rows of this matrix are a scalar multiple. One row is a scalar multiple of the other. So there's infinitely many solutions to that. Now, the one thing though is that one thing I can get from A, or from this bottom equation, is that A equals the opposite of B, or vice versa, B equals opposite of A, however you like. Okay? Now, if I chose A equals 1, then B is negative 1. But this equation is the same thing. If I chose A equals 2, then B is negative 2. It would still be a solution. So there's an infinitely many choices for A. B would be determined. But one thing that would be true is that every vector, A, B, that we get would just be a scalar multiple of each other. Okay? So it would be, that's like, I can just choose one of them for A and pick one of the eigenvectors corresponding to lambda equals 2. Okay? So, A equals opposite of B. If I choose A equaling 1,
You just choose n. Like,
anything, yeah.
just make it general since now we do it anyway.
Yeah, but we can pick
Are
one.
we trying to be specific?
We might as well pick the simplest one, because when we find a solution, what we're going to be doing is finding solutions for the system, a scalar multiple outside it. When we find the general solution, the superposition, a scalar multiple is not going to matter which eigenvector I choose if they're all scalar multiples of each other. So that scalar multiple is just going to get absorbed anyway. So you can make it as simple as possible. Choose A equals 1. Then this eigenvector, and I'll call it V sub 1 here, because we're going to have another one, right? So this would be, if I chose A equals 1, then what's B? Negative 1. Okay? So that is an eigenvector corresponding to the eigenvalue of 2. Of course, I could have chosen 2 for A, and B would be negative 2. If I chose 10 for A, B would be negative 10. But they'd all be scalar multiples of this vector. So essentially the same vector, but just scaled. They'd all be parallel. Okay? So we could pick the simplest one, and plus, like I said before, any constant multiple, when we throw this into the general solution of the system, there's going to be constant multiples times our solution. So it doesn't matter what multiple I choose. Okay? All right. So one thing you could do, check that that's true. And I'm just going to do this on the sideboard. Oh, wait, yeah. And lambda was,
2.
lambda was 2, and we got V1 was 1, negative 1. So check this out. What was our original matrix A?
4, 2, 1, 3.
4, 2, 1, 3.
Jesus.
4, 2, 1, 3. So that's A. Multiply that by our eigenvector, 1, negative 1. And let's see what we get.
Actually, wouldn't it need to be 2, negative 2? Or,
Oh, these guys?
no, the vector.
Oh, watch. We're wondering, so is it equal to, we got 2 for the eigenvalue, is it equal to 2 times 1, negative 1? That's what we're checking. The scalar A times V, does it actually equal 2 times V? So that's the original definition of an eigenvalue and eigenvector. So if I multiply these, what do I get? 4 minus 2 is 2. 1 minus 3, negative 2. And that is exactly a scalar multiple of that vector, my original eigenvector. So a V does equal 2 times V, scalar multiple of that vector that goes into it. So that's the definition of an eigenvector, eigenvalue. Let's find the other one. We had one corresponding, we had 2 and 5 for our eigenvalues. So let's take the other one, lambda equals 5. And take my original, A minus lambda I. So we had 5. So my matrix would be 4 minus lambda, 2, 1, 3 minus lambda. Right? It was 4, 2, 1, 3. And we want to know, I'm going to call these constants C and D the entries of this one. And this is what we're looking for. We're looking for the other eigenvector corresponding to 5. Okay? All right. So what equation does this give me here? 4 minus 5 is negative 1. That would be negative C plus 2D would have to equal 0. And C minus 2D equals 0. Oops. C, not 2. C minus 2D equals 0. So again, are these equations dependent?
Yeah, they're gonna go to 0.
Oh yeah. The bottom one is a scalar multiple, negative 1 times the top. Okay, so there would be infinitely many solutions, but they would come. Of course, it's linearly dependent because that's where we made it. We found the lambda that made that happen. So this is linearly dependent equations. Oops. All right. But one thing I can say is that C equals 2D from equation 2 here. So we can find a particular vector by taking C to be, well, whatever we want, or D to be whatever we want. So take D equal to 1. Then C is 2 times that. C would be equal to 2, right? So our vector, our eigenvector corresponding to the eigenvalue 5.
Give it backwards.
If D is 1, C is 2 times D.
Oh,
2
sorry.
times 1 is...
Yeah, I had it backwards.
Yeah. So CD would be 2, 1. Okay? Or any scalar multiple of that, because if I chose D equals 5, C would be 10. So 5, 10 for D and C. 5, 10. So any scalar multiple of this would also be considered an eigenvector corresponding to 5. But you can think of this as like the principal one or the simplest one. If I put 1 as one of those guys, one of those entries.
Smaller prime factors.
Yeah. So the question is, what is all this? What are we doing with all this?
We're just
All right.
algebraing ourselves in circles here.
Wait, this isn't linear algebra?
Right.
I think.
How is this relevant
Anything.
to systems of DEs, systems of differential equations?
It's all the same. Calculus, differentials, linear, algebra. It's really just one math. They just.
So if you look at 5.2, it's entitled the eigenvalue method of solving a system of differential equations. Okay, and we're going to start simple with the constant coefficients in front of the, in these systems. So constant coefficient functions. So consider the system say x bar prime equals px. We call that equation 5. Where P is that matrix we were working with before, 4, 2, 1, 3. Okay. So this is going to be parallel, kind of parallel to our work with single differential equations. Okay, so not a system, but you know how in single differential equation we assumed that. And if I was calling my dependent variable x, we, or whatever, x double prime minus 2x prime plus 3x equals 0. If we had a homogeneous system there, we assumed the form, what?
Y equals R, or X equals.
Right, in this case it would be x equals, and if the independent variable is t, we assumed x equals e to the rt, okay? And r represented, well, a real value, and when we plug it into there, we got what's called a characteristic equation we solve for r, right? Okay, the parallel to that in a system is we're going to be hunting for eigenvalues, okay, that make that true, that work. So assume the form x bar for the solution as e to the lambda t times some vector v, and that vector v is going to be a vector of constants because our function x, this is a vector of functions. So e to the pi t would just be a single real value. This is a vector. So I have e to the pi t times every entry in that vector.
Pi.
Pi, lambda?
What did I say?
Pi.
I said pi?
Yeah,
Yeah.
twice.
V. All right. So many things going around. Okay, so this is a similar form. E to the lambda t would be just a single real value. This fills it out because that's a vector quantity, and I'd have one for each component. And so this is again a vector function if I multiply e to the lambda t in each component. So what we want to do is find the values of that happen, find the values of lambda and v. Okay. So this is analogous to our work with single higher order differential equations. And they go through a fine argument in the book about why this works. Okay, similar to this. Okay. All right. So if we assume that form, let's see what results. All right. So if we differentiate that, x bar prime. Well, the derivative of a vector function is the derivative of each component, right? And that part of it on the outside is just going to be lambda e to the lambda t, and that is a vector of constants. Okay, so if you do that in each component, lambda pops out, e to the lambda t times v. Okay. All right. And pull this lambda out, and I'm going to write it this way for a moment, e to the lambda t v, and we recognize this as x again. Okay. So in other words, x bar prime equals lambda x bar. So equation 5 then put this in for x bar, or sorry, oh right, in equation 5, substitute for x prime this part right here. We get lambda x bar equals p x bar. Okay, and from that, if I subtract on the other side, subtract both sides, or the left side from the right, we'd have px minus lambda x equals 0. And this would yield right multiplication by x bar, p minus, I want lambda I. Throw in an I there, it's like 1. P minus lambda I, x bar equals 0. Okay? So therefore we are interested in finding the eigenvalues corresponding to the matrix P, the coefficient matrix. So basically, we search for the eigenvalues and the corresponding eigenvectors of the coefficient matrix P. Okay. And that's called the eigenvector or eigenvalue method of solving a system. Okay. Let's going back to that example. So we found in our previous example